So the next talk is by Ashish Chiplunkar, and he's going to talk about the curious case of the weighted K-server problem. A fascinating title. Ashish tells.
Okay. Am I audible? Okay. Thanks a lot to the organizers for inviting me as a speaker to this workshop. Uh, Let me tell you right in the beginning that I expect you to ask lots of questions. Otherwise, the talk is going to be short. So unless you are extremely hungry and you want an early lunch, feel free to stop and ask questions. Okay, so this talk is going to be about the weighted K-server problem. But before we go to the weighted K-server problem, let's first see what is the unweighted K-server problem. Probably some of you are already aware of this problem. Right, so the problem is defined on a metric space. So metric space is just a set with a distance function that satisfies the triangle inequality. So we have some k identical servers sitting at points on the metric space. And then in each round, we get a request at a certain point, and we need to serve this request by sending one of the servers to the requested point. Okay, and this happens over and over again, right? So what do we want to optimize over here? We want to optimize the total movement of the servers, the total distance traveled by the servers. But obviously, as defined, this is an online problem, right? So you at the time of deciding which server to send to serve a request, you are not aware of the future requests, and therefore it's unlikely that you will actually produce the optimal solution to this instance. So therefore, we given an algorithm, we determine how good it is by comparing its performance against the optimal solution to a given instance. So we define the competitive ratio of the algorithm as the worst case ratio between the expectation of the algorithm's cost to the optimum cost. Okay, so what was known about this about the K-server problem? Well, the K-server problem is considered one of the cornerstones problems in online computation, and it has been studied for the last more than 3 decades now. And even before I started going to school, it was already known that no deterministic algorithm can have a competitive ratio strictly less than k, provided the metric space is large enough, right? So if the metric space itself is small, then you can just put one server on every point and then you're done, right? So if as soon as the metric space has more than k points, no deterministic algorithm can have a competitive ratio better than k. And the proof is rather simple. The proof is just take any k plus 1 points in that metric space. One of them is guaranteed to be not occupied by the algorithm servers. Just give a server, give a request at that point and repeat. That's it. Okay, and then what is known from the algorithmic side? We know that a certain algorithm called a work function algorithm achieves a competitive ratio which is like a factor 2 off from the lower bound. It achieves a competitive ratio of 2k minus 1. And since 1995, it's an open problem to determine what is the correct deterministic competitive ratio, what is the best possible ratio, and it is conjectured that actually there exists a k competitive algorithm for the weighted for the k server problem on any metric, for the unweighted k server problem. So this is famously called the deterministic k server conjecture. Okay, so if we expand our set of algorithms and allow randomization, well, we know that, well, it has been known since a long time that no randomized algorithm can have a competitive ratio which is strictly less than hk. What is hk? Hk is just the kth harmonic number, roughly natural log of k. Okay. And it was also conjectured that actually there exists an algorithm whose competitive ratio is like log k on every metric space, but only very recently, less than about a month ago, this has been proven to be false. I'm yet to read the proof. So the Bubek et al. Claim that actually on a certain appropriately defined metric space, the competitive ratio is like omega of log squared k. Okay. So that way the conjecture has been proven to be false. But then from the algorithmic side, there were a couple of papers in 2018 which claimed that there is a randomized algorithm with competitive ratio which is like polylogarithmic in k, but apparently some mistakes were found in those papers, and to the best of my knowledge, the deterministic 2k minus 1 bound is the best possible, is the best known bound, even if we allow randomization. So no better bound is known with randomization. So this is the state of the art as far as the unweighted k-server problem is concerned. So what is the weighted k-server problem now? So in the weighted k-server problem, the only difference is that the servers have weights now. So there is a big server, there is a small server, okay, and so on. And so if a server moves through a distance d, the contribution of that movement to the cost is d times the weight of the server. Okay, so earlier it was just the summation of the weights. Now it is a weighted total movement. Yeah. So what is an obvious algorithm for the weighted k-server problem? Well, the first one, the first algorithm which you should probably come to your mind is, let's just take any algorithm for the unweighted k-server problem and blindly use it, completely ignoring the weights. Okay, very naive idea. And this still achieves a competitive ratio, which is like the largest weight divided by the smallest weight times the competitive ratio of the algorithm, of the unweighted k-server algorithm. So this is simple. If you imagine that, if you conservatively assume that every time your algorithm moves, it is moving the heaviest server, whereas every time the optimum solution moves the server, it is moving the lightest server. Just due to that conservative assumption, you get this kind of a result. But then these weights are arbitrary, right? So that is why we are not really happy with this. What we really want is bounds on the competitive ratio which are independent of the weights involved in the problem. Okay, and also we want them to be metric space independent, obviously. Why? Because otherwise the problem will kind of reduce to something called a uniform metric where all distances are one, and then you'll simply multiply the competitive ratio by the largest distance by the smallest distance, something like that. Okay, so what we want is a competitive ratio which is just a function of k, no matter what the metric space is, no matter what the weights are. Okay, any question as far as this problem definition is concerned? Yeah. Can you be louder? I can't hear it. What if you allow logarithmic dependence on the aspect ratio? Oh, I see. I'm not too sure about that. But there is a good reason. I'm not too sure about that, and that will be very clear in an upcoming slide. Okay, so what is known about the weighted k-server problem now, right? So I claim that this weighted k-server problem, in spite of it might look as if that it's a little modification to the k-server problem by introducing the weights, innocuous looking modification, but I claim that this makes the problem incredibly hard. Okay, why do I say so? Well, consider the weighted 3-server problem, right? You just have 3 servers in your metric space. Metric space is arbitrary. Let's say W1, W2, W3 are the weights. Now my question is, can I give a constant C independent of the weights such that no matter what the metric space is, there is a C competitive algorithm for the weighted 3-server problem, okay, on that metric space. This is open. Okay, so forget about logarithmic dependence on the metric space and so on. We don't even know, right? We don't seem to have any good ideas on how do you design an algorithm for this problem on as soon as you have like 3 or more servers. Okay, so open problem. Okay, yeah. Exactly, yes. So for two servers, as soon as I have two servers, well, there is something known, right? So bound on the competitive ratio is known, but it's already a 4-digit number. Okay. Whereas if you recall, the in case of the unweighted K server problem, the for K equal to 2, the bound will turn out to be 3. Actually, if I remember correctly, for the specific case of 2, you actually have a 2 competitive algorithm for the unweighted K server problem. But yeah, this is pretty bad. And so in this sense, the problem is hard, and the problem is also hard in another sense. It's hard in the following sense. Uh, we are not able to think of approaches to attack this problem. Why do I say so? Because even for K equal to 2, any guess on what would be, what is the best known lower bound on the competitive ratio? Any guess from the audience? Let's just guess the number of digits in the 1 digit. Yeah, absolutely. Yeah. So okay. So if you restrict your attention to deterministic algorithms, all we know for now is that you cannot have an algorithm whose competitive ratio is strictly better than 5. Yeah. Louder. Yes, the upper bound is deterministic. Okay. I believe if we allow randomization, then this lower bound goes further down, but it's still slightly more than 2. One of my students worked on this bound, so although we haven't really published it anywhere. Okay, so in this sense, the weighted K server problem is hard. So if the weighted K server problem is hard in the full generality, let's consider this problem on simple metric spaces. Let's at least focus on simple metrics. What do I mean by a simple metric? We will focus on the uniform metric. Okay, uniform metric is the metric space in which the distance between every pair of distinct points is 1. Okay, so that's a simple metric. Okay, so if we focus on the uniform metric, then the unweighted K server problem turns out to be equivalent to a very well-known online problem, which is called the paging problem. So what is the paging problem? Imagine that you have this slow memory, which consists of a huge number of pages, and the processor is accessing, requesting you to access certain pages in this memory. But the processor can access the page only if the page is present in the fast memory, not otherwise. So therefore, if the processor wants to access this pink colored page, then somehow it needs to be brought into the fast memory by throwing away one of the existing pages in the fast memory. Okay, so this page replacement is what we want to minimize. And if you think of the the pages in the slow memory as points in the metric space, all with a pairwise distance of 1. And if you think of the slots in the fast memory as your K servers, this turns out to be the unweighted K server problem on a uniform metric. Okay, so what will the weighted K server problem on the uniform metric turn out to be? Well, it will turn out to be this variant where each of the slots in the fast memory has a weight, and that is the cost you incur when you replace a page in that slot. Okay, so what is known about this problem now? What is known about the weighted K server problem on uniform metrics and the unweighted K server problem? So for the unweighted K server problem, we know for a long time that certain policies such as least recently used, first in, first out, and so on, they turn out to be all K competitive. Okay, and this is obviously optimal because we saw earlier that as soon as your metric space has K plus 1 or more points, you cannot hope to be better than K competitive if your algorithm is deterministic. So if you allow randomization, we know an algorithm whose competitive ratio is roughly log K, okay, and that also turns out to be optimal. So in this sense, we have a full understanding of the unweighted K server problem on uniform metric spaces. What about the weighted K-server problem? So in the seminal paper by Fiat and Ricklin, which introduced the, so this lower bound of K holds for any metric space which has at least K plus 1 points. Okay, so in particular, it also holds for uniform metrics. Okay, so in the seminal paper by Fiat and Ricklin, they proved an doubly exponential upper bound on the deterministic competitive ratio. Okay, yeah, so the idea behind this algorithm, high level idea is pretty intuitive, I would say. What do? You pretend that as if the heaviest server does not exist, and you serve the request using the K-1 lighter server in a recursive manner. Okay, you collect information. You collect information about the more frequently requested points until the total cost of your algorithm becomes like some constant times the weight of the heaviest server, and then you move the heaviest server to the most frequently requested point. In some sense, on a high level, this is the very basic idea, and then you keep on repeating this. Okay, so this lower bound of K plus 1 factorial by 2 is also pretty intuitive. Again, the idea is same. Take any K plus 1 points in your metric space. Okay, so one of them is guaranteed to be not occupied by the algorithm server. Give a request there. So where does the K plus 1 factorial come from? The K plus 1 factorial term comes from the fact that since the servers are distinct, the number of possible ways of arranging those K servers on K plus 1 points is K plus 1 factorial. Okay, so therefore, by the time the algorithm manages to guess the optimal configuration, it already loses this kind of a factor, and therefore that becomes a lower bound on the competitive ratio. Okay. Yeah, so this remained the state of the art for a long time until Bansal et al. In 2018 improved this lower bound, which was singly exponential, to a doubly exponential lower bound. Okay, so the constants hidden in the big O and the omega are different, so the bounds are quite a big factor off, but at least up to the number of orders of exponentiation, they are the same. So that is in some sense a good news. What if we allow randomized algorithms, okay, for the weighted K-server problem on uniform metric spaces? Until the end of 2020, the best known upper bound was still doubly exponential. Okay, and I'm going to briefly go over the idea behind this algorithm because it is one of my work. So in spite of the randomization, no improvement over the deterministic bound except for the number sitting in the as the bottommost base. Okay, and what about the lower bound? Embarrassingly, we did not know any lower bound better than log K. Okay, so there was a huge 3 orders of exponentiation gap between the known upper and lower bounds. But in 2021, in a joint work with one of my students, we proved an exponential, singly exponential lower bound on the competitive ratio. So in that way, the gap has reduced to a single order of exponentiation now. Okay, how much time do I have? I've lost track of time. Sorry? Oh, that's perfect. Okay. So what I plan to do in the remainder of this talk is I will spend a little time on the idea behind this algorithm, the doubly exponential randomized algorithm, and then I'll suggest one promising in my opinion, promising approach of attacking this problem and hopefully coming up with an algorithm with a singly exponential competitive ratio. Any questions so far while I take a sip of water? There's no water. Okay, fine. So if there are no questions, let's continue. So right, so what is the first algorithm that would come to your mind for the weighted K-server problem if I allow you randomization? Any suggestions? Very simple idea, very simple. So simple that I could call it stupid, but still it works. Uniformly random server, well, you have weights, right? Sorry, proportional to the weights, exactly, yeah. So that is the idea, right? It's a randomized memoryless algorithm. So what is a randomized memoryless algorithm? Well, as the name suggests, it doesn't have memory, it doesn't keep track of the history. Okay, so it has a fixed probability distribution hard coded into it, which depends on the weights of the servers. Okay, and whenever necessary, whenever it finds that the requested point is not occupied by its servers, it will sample one server from this probability distribution and move it to the requested point. As simple as that. Okay, so this is simple and efficient because you don't have to keep tracking the history. You don't have to do any kind of computation on the history. Just toss an appropriate number of coins and then you're done in every step. But is it competitive? Well, in 2004, right, for k equal to 2, this was shown to be competitive and have a competitive ratio of 5. And as Pravesh said, the idea is pretty simple. Well, your probability of moving a server is inversely proportional to the weight, okay? Except that you have to have the denominator so that the probabilities add to 1. That's all. Okay, where do these constants 3 and 2 come from? Well, they have been adjusted in order to minimize the competitive ratio. Even if I put arbitrary constants there, I'm going to get a constant competitive ratio independent of the weights. Okay, it was also known at that point of time that no randomized memoryless algorithm has a better competitive ratio than 5. But this is for k equal to 2. What about arbitrary k? Okay, so for arbitrary k, we managed to extend the ideas of this analysis and prove the following claim. Okay, so let's first define this sequence alpha k iteratively, where alpha k is defined as a quadratic polynomial in terms of alpha k minus 1. Okay, so therefore the dependence of alpha k on k becomes doubly exponential. Okay, and we claim the following. Okay, you give me any k, you give me any set of weights w1 through wk, I can come up with a probability distribution, okay, p1 through pk, such that the corresponding randomized memoryless algorithm achieves a competitive ratio of at most alpha k. Okay, it's pretty, I would say it's an extension of the same idea, but creates a lot of complications in the proof, although. So what probabilities do we choose? Again, the probabilities, each probability pi is inversely proportional to the weight wi. Again, except modulo the denominator, which appears because all the probabilities have to sum to 1. Okay, so what are these constants C1 through Ck? They are absolute constants independent of the weights. And they can be computed by some kind of a recurrence, although I forget the recurrence now. Okay, moreover, this bound of alpha k also turns out to be a tight bound. You cannot get a better randomized memoryless algorithm. I'm not saying in an asymptotic sense, I'm saying alpha k is the bound, is the best possible ratio. Okay, but some terms and conditions apply. Terms and conditions in the sense that the adversary, the model of the adversary we consider is slightly harder than the classical oblivious adversary. Okay, nevertheless. So this was the doubly, this is the, yeah, till date, this is the best known doubly exponential algorithm, randomized algorithm for the weighted k-server problem on uniform metrics. So what I'm going to do in the remainder of the talk is discuss a possible approach for improving this bound and hopefully get a singly exponential bound. Sorry? Yeah. Yes, that's right. Okay. Yeah. Yeah. Hmm. Yes. Yes. It's a marking, right? It's a marking algorithm. So that is where you use memory. Okay, good. Uh, yeah. So weighted K server on uniform metrics, we saw till now that if you are not allowed to use memory, but you are allowed randomness, that's not enough. Your competitive ratio is still doubly exponential. If you're allowed to use memory but not randomness, which means your algorithm is deterministic, well, your competitive ratio is still doubly exponential. So the question is, suppose you are allowed both randomness as well as memory. Okay, how much does your competitive ratio improve? Okay, yeah. Is it still hard on non-uniform metrics? So on non-uniform metrics, we don't even know an algorithm, right? For k equal to 3 or more, right? So for the unweighted K server problem, we know an algorithm with competitive ratio linear in K. Okay, so I need to define a couple of terms before that, before we see the approach, which hopefully will lead to a better algorithm. So this is what Bansal et al. Suggested, right? So think of the solution of an instance as something called service pattern plus labeling. I'm going to explain these terms. So consider a sequence of requests, okay? And consider an arbitrary solution which serves the requests, okay? Focus on the movements of any one server. Let's say the lightest server, okay? So this, what do I mean by this? So what I've done is I have partitioned the time axis into intervals, right? And so the boundaries between the two intervals are the time instants at which the server moves from one point to another. Okay, so the movements of every server induce a partition of the time axis into intervals. Okay, and let's do that for every server. So what you get out of it is k partitions of the time axis into intervals, and such a couple of partitions is called a service pattern. Okay, so what is a labeling of a service pattern now? So labeling of a service pattern tells you right, so it's a label given to every interval appearing in the service pattern, and the label tells you where the corresponding server was for the time in that lying in that interval. Okay, so now this will completely specify a solution to any instance of the problem, and the cost of the solution is just a function of the service pattern. It only depends on how many times every server moves. Okay, so it is independent of the labeling of the service pattern. Okay. Now, when do I call a labeling feasible? I call a labeling feasible if the resulting solution actually serves all the requests. What does that mean? It means that for every request R, I should be able to find one of the servers such that the unique interval in that partition which covers the request is actually colored with the same color as the request, or is labeled with the request in that sense. Okay, so that is a feasible labeling, and in a natural manner, we define a service pattern to be feasible if it has at least one feasible labeling. Okay, so the idea behind hopefully getting a better algorithm is to decompose the weighted K server problem into two fairly natural relaxations of the problem. Okay, so let me define the relaxations now. So in the first relaxation, well, the input is still a sequence of requests, but what you are expected to output is just a service pattern, not a labeling of a service pattern. As long as the service pattern which you output is feasible for the request sequence, that is good enough. Okay, so you output an unlabeled service pattern. Another way to think of this is that you output the service pattern in an online manner, and then at the end you color, you label every interval in the service pattern in a feasible manner. The challenge is to output a service pattern that remains feasible after every request. Okay, and obviously you cannot go back and change what you have done already. Okay, the goal is to compete with the cost of the optimum solution. This is the first relaxation. Clearly, this is this can be only easier than the weighted k-server problem, right? Because I can use a weighted k-server problem algorithm over here and not output the labeling of the service pattern, output only the service pattern. So here is another relaxation of this problem. So in this relaxation, our adversary is helpful to us. Okay, so in addition to the requests, the adversary also gives us a feasible service pattern as input, as additional help. Remember, the pattern given to us is unlabeled, but it is guaranteed to be feasible, which means it is guaranteed to have one feasible labeling at least. Okay, and your job is to serve the requests, right? Or equivalently is to output a service pattern and a feasible labeling of that service pattern. Okay, what do you compete against? You compete not against the cost of the optimum solution to the instance, but you compete against the cost of the unlabeled service pattern given to you. Okay, so remember, the unlabeled service pattern given to you need not be an optimal service pattern. It is some feasible service pattern, and you're only required to compete against it. Okay, so what does that mean? If the adversary really decides not to be helpful and gives you a very suboptimal service pattern to you, well, you can be equally suboptimal. As long as you can compete well with the service pattern given to you, that's good enough. Okay, so why have I defined these relaxations? Well, it turns out that as soon as you construct algorithms for these two relaxations, you actually have an algorithm for the weighted k-server problem. I think this proof might be obvious to some of you. What do we do? How do we construct that algorithm? Huh? Okay, product. I guess you meant compose the two algorithms together. Yeah, exactly. Yeah. So yeah. How do we go about it? Well, we are given a sequence of requests. Of course, this is an online sequence, although I've given all the requests to you right now. Right. So you give these requests to an algorithm for the first relaxation, which is only required to output a feasible service pattern. Now an algorithm for the second relaxation comes into picture. It takes both the request sequence and the feasible service pattern as an input, and it outputs its own solution. Okay, and what do we do now? So we put together algorithms A1 and A2, and that way we get an algorithm A for the weighted k-server problem. Okay, how good is this algorithm A? Well, if we assume that the algorithm A1 is alpha 1 competitive, what are we guaranteed? We are guaranteed that the cost of the service pattern output by A1 is at most alpha 1 times the optimum. If we assume that the second algorithm A2 is some alpha 2 competitive, what that tells us is the cost of the final solution is at most the cost of this intermediate service pattern, right? So cost 2 is at most alpha 2 times the cost of this service pattern, which is at most alpha 1 times the optimum, right? So therefore, the cost of the overall solution output by the algorithm is at most alpha 1 alpha 2 times the optimum. Right, so what does that mean? It means that if I compose these two algorithms together, I get an algorithm whose competitive ratio is alpha 1 times alpha 2. Yeah. Sure. Right, so the service pattern output by A2 could be different from the service pattern input into A2. right? That is allowed. Yeah. So in the second relaxation, I'm not required to label the service pattern given to me. I'm allowed to output any service pattern and any labeling, provided it serves all the requests. Okay, I don't think it's possible to label a given service pattern in an online manner. That would be very unlikely. Okay, so now what is our job now? Now our job is to get hopefully a singly exponential algorithm for A1, get a singly exponential algorithm for A2, and then put them together to solve the problem, to get a singly exponential algorithm for the weighted k-server problem. Where are we right now? Right, for the second relaxation, we do have a singly exponential algorithm. So this is some unpublished work, unfortunately. Yeah. So the competitive ratio is like 2 to the power k squared, not 2 to the power order k, but that's okay because it is singly exponential still. Okay. In fact, it turns out that the lower bound of 2 to the power k, which I mentioned earlier for the weighted k-server problem, also holds for this relaxation. Okay. What does that mean? It essentially means that in the lower bound construction, we have managed to capture the hardness involved in relaxation 2 only. Why? Because for relaxation 1, we don't know an algorithm and neither do we know a lower bound. Okay, so for relaxation 1, it's an open problem to design a 2 to the poly k competitive algorithm. And if you manage to do that, by composing the two algorithms together, you will get a 2 to the poly k competitive algorithm for the weighted k-server problem on uniform metrics. But unfortunately, we don't even know a lower bound for this relaxation 1, that super constant lower bound, let's say, that increases with k, right? So in that sense, in the omega 2 to the power k lower bound construction, we have only captured the hardness involved in relaxation 2, and we have absolutely no idea of the hardness involved in relaxation 1, hardness that relaxation 1 contributes to the problem. So it is possible that relaxation 1, in fact, it's hard to compete within a factor doubly exponential in k. Who knows? Right? But we have no idea of what kind of hardness is involved in relaxation 1 itself. Okay. Yeah, that's it from my side. Questions? Yeah, Rohit. Yes, everything is online, right? So let's go back. Right. So in every round, you are given a request and you're also told how is the unlabeled service pattern kind of extending, right? One request further. Okay. And then you need to output a solution, right? You are not, it's not necessary that you only label the service pattern given to you. You could output your own service pattern.
I would just ignore that guy.
Exactly. Yes, in that sense, yeah. So as Anupam rightly pointed out, if you had an algorithm for the weighted k-server problem, you could just ignore the service pattern given to you and output your solution, right? So in that sense, there's a relaxation. Yeah. Right. Yes. Yes, but it is helping you by giving you a service pattern. Yeah. Yeah. Sorry, I couldn't hear that. Maybe use the microphone.
Yeah, so if you make some distributional assumptions on future requests, can you do better for k-servers? Is that better competitive?
I don't think such kind of results are known. Although I believe such kind of results are known for the unweighted k-server problem. Yeah. have people studied the possibility of dropping some requests? Hello? Okay. Yeah, not explicitly, but if you look at the deterministic doubly exponential upper bound proof, the proof goes through dropping some requests and so on. It needs to make that assumption that the adversary is able to drop some requests and so on. Still, your algorithm is able to compete, right? So it's an inductive argument, and this business of dropping requests is essential to make the induction hypothesis stronger so that the inductive proofs works. Yeah. We don't know anything beyond the uniform metric for k greater than k greater than or equal to 3, except for the obvious bound, which depends on the aspect ratio of the metric, maximum to minimum distance. Sorry? Even in R2. Even in R2. Yep. Sorry? Probably. Yeah, I'm not too sure about this. Well, forget R2, even on R1, even on the line metric, all we know is that a randomized memorized algorithm cannot have a finite competitive ratio. That's all we know. Even for k equal to 2.